So today, hopefully, we are going to derive something called the Fokker-Plank equation, and then we may look at its uses in physics, if there's time, or I may put that in a separate video. We'll see. Anyway, we are going to begin with the fundamental definition of a Markov process. So we'll start off with the these names are going to get me today. The Chapman-Kolmogorov equation. So we can say that P of x plus x and t plus tau, which is going to be that small t thing. We'll say that's tau. So you to the integral from minus infinity to infinity of w of x bar x prime and tau, multiplied by p of x prime tau dx prime. And so, well, what does that mean? So w x bar x prime, basically w, that function, is the transition probability density of jumping from state x prime to state x in time interval tau. So what this equation is doing is it's giving us the probability, or rather it's saying what the most likely state of the most likely future state of some process x, some Markov process, is with probability density. God, let's start again. So, this is saying that the probability density of process x at time t plus tau is related to the sum over all of the intermediate steps beforehand. So that would be x prime, which is the step, the state that we know. So we can introduce a jump variable here, and we can call it delta. And delta is x minus x prime, so that's the jump between our current state and our predicted state and the known state. X prime, therefore, just simple algebraic rearrange, is x minus delta, and dx prime is equal to minus d delta, and we can say that from integrating both sides and then moving it over with respect to delta. Differentiating. Yeah, differentiating, sorry. So, oh dear, what's going on? We know a couple of things from this. We know that as x prime tends to minus infinity, delta tends to infinity, and further, when x prime tends to infinity, delta tends to minus infinity. There you go. So that's what we know so far. We can sub all of this information back in, because this is setting up our bounds. We can sub this back into the original equation, which is the Chapman-Kolmogorov equation, and we get that p of x t plus tau equal to that integral from minus infinity to infinity of w of x bar x minus delta tau, and multiplied by p of x minus delta. This is just by our substitution of what x prime is equal to up there, and then minus d delta, which is equal to the integral from minus infinity to infinity of w x bar x minus delta tau, and then p of x minus delta t d delta. Very cool, very cool. Now what we'll do is we'll take this composite function inside and we'll define it as f of x prime delta being equal to w of x bar x prime tau p of x prime t, and that's our new function, capital F. But we specifically want to expand the dependence on the starting position x prime, so up here, x prime is x minus delta around 5 x. So we can use a Taylor series expansion for a function f of x minus delta, which is x prime. And that's equal to the sum from n equals 0 to infinity of minus delta to the n. That's minus delta to the n over n factorial partial, the nth partial derivative of f of x over the nth derivative of x, or over, yeah, that, the nth partial derivative of f of x, basically. And now we can apply this to that capital F, or rather just the integrand in general. And so we can say that f of x prime delta, oh, that's not right, sorry. We can say that, not this, we can say that w of x bar x minus delta t is equal to the sum from n equals 0 to infinity of basically that applied to that. So I'll just write that again. Minus delta n factorial, and it's derivative of f of x. Sorry, not, well, f of x is our dat, so over partial x n of, we can just put that in bracket, w of x bar x. Actually, this would just be of f of x prime delta, and that's our new integrand, and we might then push this back into our original equation, which we have above, which is the Chapman-Kolmogorov equation that we've expanded with our final Taylor series expansion to say that p of x t plus tau equals to this integral from minus infinity to infinity of that the sum from n equals 0 to infinity of minus 1 to the n delta to the n over n factorial, and then the nth derivative of f. You can actually just write that d delta, and of course we have limits and sums, and we can pull stuff out, and we have a constant that doesn't depend on the integrand, so of the variable. So we can say that this is the sum from n equals 0 to infinity of minus 1 to the n over n factorial times the integral from minus infinity. That was a nice integral. These are not nice infinities. Delta to the n, of course that delta depends, so we can kind of split that down there, because it's just fraction, times the nth derivative of f, x to the n d delta, and that is our Taylor series expansion of our probability density equation. That's supposed to be an integral. What on earth is that line? Sorry, that's supposed to be little f. There we go. Oh, the handwriting is bad. It's okay. It's okay. Now, what's crucial is this partial derivative is with respect to x, but this is with respect to delta, so we can actually take that out, and we can take all of that out, to be honest, which is then equal to n equals 0 minus 1 to the n over n factorial, and then the partial derivative of p of x t times that integral from minus infinity to infinity of delta to the n I realize that may not be, yeah, no, sorry, that should not be f. It's okay. We will continue it from down here correctly. This would not be f. This would in fact be w of x plus delta. W of x plus delta bar x comma tau d delta. Mistakes will always be made when maths is this abstract, I think. Apologies for that. Yeah, I do need a bracket there. Cool. Now what we can do is we can define the nth conditional moment of jump size delta. So if we let y equal to x plus delta, that's our final position, then delta equals y minus x, d delta equals dy, and then the integral from above will become, or rather the integral inside the sum, which is the integral from minus infinity to infinity of delta to the n w of x plus delta bar x tau d delta is equal to the integral from minus infinity to infinity of y minus x to the n w of y bar x comma tau dy is equal to we can just call this m sub n of x tau, which is the expected value of the jump, which is useful. So we can define this further. M sub n of x tau. That's my tau. I think it's evolved a bit, but hopefully you know what that means. Bring in some bracket notation. Hopefully that's clear. These are going to be really bad. Sorry. Of x t plus tau minus big X of t all to the n, and x of t at this point equals x, and we can sub this m sub n back into our expression from before, and hence I can't find it. Where is it? There, somewhere over here. There it is. Back into our expression from before, and say that p of x t plus tau is equal to the sum from n equals 0 to infinity of minus 1 to the n over n factorial partial nth partial of, we can do the square bracket, I don't mind, sub n of x tau p x t. What we're going to do now is separate the first terms from the rest of the sum. So we'll calculate n equals 0 first. So n equals 0 would of course be minus 1 to the 0 over 0 factorial, and then the 0th derivative of m sub 0 of x tau p of x t, which is just m of 0 x tau p of, oh no, what's going on there? Tau p, oh, it's just not claiming that they exist. Got it? Still thinks they don't exist. Love that. Good software, Microsoft. M sub O of x tau p of x t. Now we can do some probability normalization. So 0th moment is just the integral of the probability density, which is 1, and hence we know that m naught of x tau is equal to this integral from minus infinity to infinity infinity of w of y bar x tau dy, which is 1. And so of course that just leaves pt. So n equals 0. We know it's pt, so we can say that p of x, comma 2. What am I about pt? xt plus tau. This should leave some recurrence relation, functional equation type of thing. Is equal to p of xt plus the sum from n equals 1 to infinity of minus 1 to the n over n factorial, all of this again, and then the nth derivative of m sub n x comma tau p of xt. So now we have, I wouldn't call it a recurrence relation, but we have a relation between the future with some time step tau, wherein the current step of our process p. Now we subtract px of t from both sides and then divide by tau, and we get that px comma t plus tau minus pxt over tau is equal to 1 over tau, really big tau, tau sum n equals 1 to infinity of minus 1 to the n over n factorial n over n x to the n times that Markov process. Cool. And what I'd like to do now is take the limit as t goes to 0. Now, what do we notice here? Hey, that looks like the definition of a derivative, right? Because the dy dx is if you take limit or d dx, we can say df of dx. Come on, I was just trying to demonstrate something. Is equal to f of x plus, I don't know, delta minus f of x over delta. Goodness me, I've forgotten the limit. Is the limit of, as delta tends towards 0, of f of x plus delta minus f of x over delta, which of course is our derivative. So by definition then we can say that that just becomes partial derivative of p, because p is a multivariable function, is equal to 1 to infinity, and on the right hand side we just get rid of, we just move the 1 over tau factor inside of our derivative, hopefully. Yeah, that'll work. So minus 1 to the n over n factorial, derivative of n over partial. Yeah, partial derivative, nth partial derivative of, now I have the limit as tau approaches 0 of m sub n of x tau over tau, and I'd really like to work out what that is, so that's what I'm going to do next, but for now we'll just finish writing that. Cool. Oh yeah, and we have to do Kramers-Moyle coefficients, so the nth d of x, which is the nth coefficient, is the limit of tau as approaches 0 of m x comma tau over n factorial tau, which is from our bracket definition up here. I'm actually going to write that on the next line because I don't want to run out of space. Is x t plus tau minus x t the nth power of that expression all over n factorial tau. We can absorb n factorial into the definition for convenience, or keep it explicit. I think the standard definition usually leaves n factorial in the Taylor sum, but we can say, just to be rigorous, we can define an of x, which is the coefficient intensity, as the limit as r approaches r. Excuse me, tau. No, it is r. Sorry, can't read my notes. Of m sub n over r. Yeah. I'm not remembering all the stuff. I do have some notes, but they're not amazing. So the next thing that we want to do is the diffusion limit. So what we're going to do is take a diffusion process driven by some Brownian motion, dwt, and we can evaluate this in x term. Get rid of that for now. So this change in x is roughly equal to mu of x tau plus sigma x change in w of t. And now we can pop that in brackets. It's equal to mu of x tau plus sigma of x change in w of t, which is just equal to mu of x tau, because this is 0. And now we can then say, since we've found that, we can define, we can define a1, which is our first coefficient intensity, of x as the limit as tau approaches 0 of mu x tau over tau, which is just mu of x, which is great. Now we can do the second moment, where n equals 2. So delta x squared roughly equal to a very long expression. Basically we square what's here, what's there even, and that should be, I didn't write this down, mu squared tau squared plus 2 mu sigma tau delta wt plus sigma squared. Yeah, there we go. Alright, we'll see if I'm right, because when we do the expectations, okay, that seems correct. Yeah, because it's just, okay, good. No, that is correct. That's not very good sigma. That's an even worse sigma. Draw pen ples. There, that's okay. So I'm really just writing out the Greek alphabet here, sigma tau. Upsilon next, please. We can say that the expected the squared, my brackets are not wonderful, is equal to mu squared tau, even worse tau, squared plus 0 plus sigma, because that term just goes to 0, because that goes to 0, plus sigma squared expected of change w tau squared, and now we can throw, sorry, this squared is just tau, by definition. That should be equal to mu squared tau. My taus are looking more like t's by the moment. Squared plus sigma squared tau. Okay, this is looking good, because this is getting towards what we're very close, basically. Very, very close. I think I'm gonna leave it here for this video. Once we've sorry, not here. Don't worry, I'm not gonna leave you in a cliffhanger. I think I'm going to just finish driving this because we're very close, and then in the next video, I'll do the rest of it, the probability in physics, the other stuff. You'll see when it comes out in a week's time. Anyway, that's fine. So now we can say that the second coefficient intensity is lim as tau goes. That was a good tau of mu squared tau squared plus sigma squared tau over tau, which is the limit as tau approaches 0 of mu squared tau plus sig. What am I doing? That's not tau. Plus sigma squared, which is just sigma squared x. And we can just introduce an extra term for some Gaussian noise for higher terms. So yn is greater than or equal to 3. The expected delta Wt in a process is roughly 0 of tau. Why is it written as c? O of tau to the n over 2. That's a 2, I promise. Now we can sub a sub 1 and a sub 2 into our expanded sum, which is somewhere, there it is, somewhere up there. And the higher terms basically decay, and we don't need to worry about them so much. So what do we get? We can say that the change in p over time is equal to minus 1 to the 1 over 1 factorial of the first partial derivative of a sub 1p plus minus 1 squared over 2 factorial times the second partial derivative of a sub 2p plus 0, they all go on to basically 0. And that yields the hopefully final equation, which is, just check that this actually makes sense. Yeah, mu of xt, p of xt plus half second derivative of sigma squared xt p plus t. That does to me look like the final Fokker-Plank equation. Alright, so to finish, I'm just going to put it in the generally written form. You'll find it in a textbook looking like this. Of p, or in fact we can do it nicely, dt of p p of xt equal to minus d dx of mu x tau t p of xt. I missed a bracket there, and there t plus the second partial derivative of sigma squared xt p of xt, and we can hopefully put a nice little box around that, and that is our completed Fokker-Plank equation, derived from, well, hopefully derived fairly rigorously from the, can I say it, the Chapman-Kolmogorov equation, with the Kramers-Mold coefficients found, and come back in a week, and hopefully you will be seeing me show the uses of this equation, surprisingly not in finance, where it's it's often important, but in physics, as we use the Onsager-Malschup action to derive the path, and the Ornstein-Uhlenbeck process. These names are wonderful. To find the probable path for a particle in a harmonic trap. So that will be very fun. Anyway, I hope you enjoyed the video, and I will see you then. Bye bye.